Okay, hello. We start again with our lecture, and in the lecture, in the next part, we will treat this topics, which is the comparison between infinitesimals and infinites. And what we want to treat here is first to recall what is an infinitesimal, what is an infinite, and what is an order of infinitesimal, an order of infinite, and the idea of principal part. All this part can seem quite technical, but remember that in the exam often we ask things about this part, and moreover it is a powerful tool in order to think of infinitesimals and infinite, and also the idea of limit. And moreover, here we will use Landau symbol in an extensive way. So be careful about that. So we start with a definition of infinitesimal. Function f is called to be an infinitesimal as x goes to x bar, f the limit for x going to x bar of f of x is equal to 0, or equivalently, if f of x is little o 1 as x goes to x bar. So this is a definition that I already introduced already at the level of sequences. And I recall you again that little o1 means infinitesimal for x going to x bar. Another definition concerns the comparison between two infinitesimals. So we start by considering two infinitesimals. Let f, g be two infinitesimals for x going to x bar. So we say that f is an infinitesimal of higher order with respect to g if f is little o of g for x going to x bar. Okay, so notice here g infinitesimal means that g is negligible with respect to 1. Okay, f is an infinitesimal too. When we say that f is an infinitesimal of higher order with respect to g, we are stating that as an infinitesimal, f is stronger than g. So f is more infinitesimal than g. So f is negligible with respect to g. Okay? So, and the problem we want to face now is the following. comparing two infinitesimals and decide which one is of higher order with respect to the other. And the problem is that, in general, comparing two infinitesimals can be a non-trivial task. So, for instance, consider these two infinitesimals. F of x is equal to the tangent of x, and g of x is equal to e exponential of x minus 1 to the square for x going to 0. Sorry, this 2 is very horrible. For x going to 0. So which infinitesimal is of higher order between f and g? This is the question we want to answer, and so it can be useful to use equivalences. So we know that the tangent of x is equivalent of x for x going to 0, and that e to the power x minus 1 is equivalent to x2, and this implies that if I consider the square of e to the power x minus 1, this will be equivalent to x squared, again for x going to 0. So as a homework, prove that. It is very easy. Let's prove that. Now the reasoning is simple now. Since x squared is of higher order than x, as x going to 0, higher order as an infinitesimal, I repeat. So it is an infinitesimal stronger than this. So it is more infinitesimal, it is more negligible than x. Okay? Then the same relationship will hold between their equivalent function. So it will happen that e to the x minus 1 to the square is more infinitesimal, so it is of higher order as an infinitesimal than tangent of x. Okay, this is the conjecture, and let me consider this limit e to the x minus 1 to the squared divided tangent of x. Due to equivalences, this is equal to the limit, so by the principle of substitution, this is equal to the limit for x going to 0 of x squared divided by x. This is 0, of course. Then, since this limit here is equal to 0 by definition of Littleow, We have that e to the x minus 1 to the squared is the law of tangent of x as x goes to 0. Then e to the x minus 1 to the square is an infinitesimal of higher order than tangent of x. Okay? So notice that here we started from a limit which is quite difficult here. There is no easy substitution or change of variable and so on and so on. But we use the equivalence to a very simple functions that here are somewhat samples. So we reduced both functions to simpler samples that can be compared easily. Okay? The strategy for comparing two infinitesimals that in general can be very complicated and difficult to compare directly. So the strategy is replace both of them by equivalent functions that are simpler and that can be compared more easily. So, in other words, provide samples to which reduce every infinitesimal. So, in general, a very a very convenient choice for a sample is given by pure powers. For instance, as in the example, phi of x is equal to x to some power alpha. But in general, one can use also different samples according to the specific problem, according to the specific infinitesimal to be compared each other. Okay, definition. So suppose that function f is equivalent to some L function phi to the power alpha for x going to x bar, with L different from 0. Okay, so L is a number, and this phi is a function. Okay, then we say first that L phi to the power alpha is the principal part. This is a very important term that we will meet again many times. This is the principal part of the function f with respect to the sample phi. Okay? Just an equivalent function. Phi, in many examples, we will have phi of x is equal to x. Okay? And moreover, there is this power alpha, and alpha, the power, is said to be the order of the function f with respect to the sample phi. Of course, both definitions, both statements hold for x going to x bar. Okay. So this is a very important definition, the principal part. And let me give some examples first. Example which is well known, we already know. We have that 1 minus cosine of x, which is an infinitesimal for x going to 0. We know that 1 minus cosine of x is equivalent to 1/2 x squared as x goes to 0. So we say, according to the previous definition, that 1/2 x squared is the principal part of 1 minus cosine of x with respect to the infinitesimal sample phi of x is equal to x as x going to 0. And of course, we can add that 1 minus cosine of x is of order 2 with respect to phi of x is equal to x, to this sample. Okay, and again, this was the first example. Then we have the second example. Again, we go back to the exercise, to the previous exercise, and we know that tangent of x is equivalent to x as x goes to 0. And this is of order 1 with respect to the sample phi of x is equal to x as x goes to 0. Okay? And so, what is the philosophy? What is the main idea underlying everything here? The main idea is that in order to compare two infinitesimals, and so to discover which one is of higher order, it can be convenient to compare their principal parts. With respect to the same sample. Okay? And okay, this is very important. So to complete the example, we can say that so 1 minus cosine of x is of order 2 with respect to x as x goes to 0. Tangent of x is of order 1 with respect to as x goes to 0. Sorry, 1 minus, yeah. So, it is correct. I was confusing myself. So, 1 minus cosine of x is of higher order, is an infinitesimal of higher order with respect to tangent of x as x goes to 0. Another example is the following: when x bar is plus infinity, for instance, a typical sample for infinitesimal is phi of x is equal to 1 over x. This is typical. When x bar is real, a typical sample for infinitesimals is x minus x bar to the alpha. Sorry, x minus x bar. And alpha would be the order. So, of course, every function, every infinitesimal can be a sample, a legal sample. So perhaps in the exam you will be asked to use another sample. Don't be scared of that. And this is for what concerns infinitesimals, but of course there are also infinites. So first of all, let me introduce what is an infinite. So the function f is called an infinite sorry here. as x goes to x bar, if the limit for x going to x bar of f of x is equal to plus infinity or to minus infinity. And here the definition of the order is the following. Let f and g be two infinites in the same point, so as x goes to x bar. Then one says that f is of higher order with respect to g as an infinite if g is negligible with respect to f as x goes to x bar. Okay? And notice here what is the difference. When we talked about infinitesimals here, we said that f is of higher order if f is negligible with respect to g, because higher order means a stronger infinitesimal, so it has to be more negligible than g. When we are talking about infinites, things changes. So f is of higher order as an infinite with respect to g if it is stronger as an infinite. So if g is negligible with respect to f. So don't get confused about that, and instead of learning it by heart, reason on it. Always reason on it. Because this reason is quite clear, so it cannot be deceptive. And of course, there is a notion of principal part again. So here the definition is the following. Let f and phi be two infinites as x goes to x bar, and suppose that f is equivalent to L phi to the power alpha as x goes to x bar, of course, with L different from 0 and alpha larger than 0. Alpha larger than 0 had to be specified also here in the other definition. Probably I forgot to do that. I'm sorry. In the definition of principal part, alpha larger than 0. Okay. Then we say first that L phi to the alpha is the principal part of f. With respect to the sample phi. And second, as before, alpha is called the order of the function f with respect to the sample phi. Okay? And of course, as a remark, we have that the definition of principal part and of order is completely identical to the analogous definition for infinitesimals. The only difference is that now the sample phi has to be an infinite and not an infinitesimal. So again, I tell you which are the most popular samples. If x bar is a real number, then again, as before, we have that for infinitesimals, phi of x is equal to x minus x bar, and for infinites, phi of x is 1 over x minus x bar. The second, if x bar is plus infinity or minus infinity, again the infinitesimals, we have that phi of x is equal to 1 over x, and infinites, phi of x is equal to x. Again, I warn you of the fact that this is just the most common choice, perhaps the simplest choice you can think of, but it is not mandatory that this will be the choice, for instance, at the exam. Okay, so read very well when we are talking about samples, which sample are we choosing for you, if possible. And the last remark says that it is not always possible to express an infinitesimal or an infinite in terms of a given sample. For instance, if you have e to the x that goes to plus infinity, for x going to plus infinity. You have that for every alpha larger than 0, e to the x divided x to the alpha goes to plus infinity, as x goes to plus infinity. Then e to the x equivalent to L x to the alpha for x going to plus infinity and L different from 0 cannot be verified. Regardless of the two quantities, L and alpha. Because otherwise, one would have e to the x divided x to the alpha tends to L as x going to x bar, which is absurd. So it is not possible to give the principal part of a given function in terms, it is not always possible to give the principal part of a given function in terms of a given sample. Okay, as an exercise which is difficult, now it is impossible to do in my opinion. I don't know a good way to do it now, but an example is find the principal part of the infinitesimal pi over 2 minus arctangent of x for x going to plus infinity with respect to the sample phi of x is equal to 1 over x. With the tools that we know now, I would not know how to solve it. But when we will study derivatives, then we will be able to do that. But just think of it, try to reason on that. If you find a method to do it with the elementary instruments that you have, I will be very happy. Show me the solution. And okay, now this is the end of this video, and the next videos will contain another part of the program, which is, in my opinion, much more exciting, and it is about continuous functions on intervals. Okay, see you.